Chapter 3 in AP Chem, we are going to be dealing with stoichiometry and mathematical calculation. So Chapter 2 pretty much reviewed all the time that we had spent naming compounds, the introduction to an atom and atomic theory. The last little bit that we have to do is we have to review the math-based portion of regular chemistry in preparation for our advanced topics that we're going to be talking about. So, if you can remember real quick, law of conservation of mass states that mass is not created nor destroyed. It was first posed by Lavoisier in 1789. Don't worry about him or that name as much, just kind of a principle. So if we look at a chemical equation, what we have here is, first off, if we look at the top, we have CH4 plus 2O2 yields carbon dioxide and water. What type of chemical reaction is this? It's a combustion reaction. We have a hydrocarbon, methane, CH4, and we have oxygen reacting to form carbon dioxide and water. Now, a couple things about the anatomy of a chemical equation. First things first, remember you have to balance the chemical equation. So in this example, we used a 2 as a coefficient out in front of oxygen and a 2 out in front of hydrogen gas to balance, or water, excuse me, to balance the equation. So we have 1 carbon, 4 hydrogens, 4 oxygens on both sides of the equation. Next up, or just a friendly reminder, reactants are on the left and products are on the right. And the arrow symbolizes a reaction, and we'll talk about the differences that the arrow can have later in the year. The states of matter and products are written in parentheses to the right of the compound. What is important is that we did not do that very much last year, and that is a very important aspect this year. So you need to remember that you're going to write CH4, and my preference is in subscript you write the state of matter. Remember, G is for gas, L is for liquid, S is for solid, and AQ is for aqueous. What is aqueous again? Aqueous is for any solution dissolved in water. So if I had salt dissolved in water, table salt is NaCl, it would be NaCl aqueous. So remember, those are kind of the 4 phases. G for gas, L for liquid, S for solid, and AQ for aqueous. And those are going to be stated in every chemical reaction for the remainder of the year. We talk about coefficients. We have coefficients, which are the numbers out in front, which describe how many of each atom we have. And then we have subscripts, which determine how many of each atom that we have in a compound. We didn't have much confusion last year, but remember not to confuse coefficients and subscripts. And if you change one, it's going to change the entire identity of the compound. So if you change a subscript, it's going to change the entire identity of the compound. If you change a coefficient, you're just going to be changing the amount. Reviewing from last year. Remember last year there are 5 reaction types. What are the 5 types of reactions we talked about last year? We talked about synthesis, decomposition, single replacement, double replacement, and combustion. Our focus is going to be on 3 of those 5. And really, we take out the replacement reactions this year, and we are focused on combination or synthesis reactions. So if you look down below, here are some examples of synthesis reactions. Magnesium burning to form magnesium oxide, nitrogen and hydrogen combining to form ammonia, and the combination of C3H6 with bromine as a liquid. So combination reactions, 2 or more elements combining together. Decomposition, one thing breaking apart. So the substance is breaking down into 1 or more things. Calcium carbonate is breaking down into calcium oxide and carbon dioxide. Potassium chlorate and oxygen. And sodium nitride into sodium and nitrogen. So just kind of a fresh example. Now remember, we'll talk about the rules of review, but carbonates love breaking down into carbon dioxide, as shown by the first example using calcium carbonate. All right, so we have synthesis or combination reactions. We have decomposition reactions. We're either combining things or breaking them apart. Then we can also be focused on combustion reactions. And combustion reactions I remember a hydrocarbon and oxygen gas, and your two byproducts are carbon dioxide and water. So usually you are dealing with a hydrocarbon in the air, and it's combusting with the oxygen that is present in the air, and you're still getting those two products of carbon dioxide and water. So after we've reviewed a little bit, here's some quick math updates. Formula weights. What is the formula weight of a compound? All right, if I wanted to ask what is the formula weight of calcium chloride? Calcium chloride is CaCl2. I'm going to take the weight of calcium, which on the periodic table is 40. Multiply it by how many atoms I have. I only have one of them. I'm then going to find the weight of chlorine on the periodic table, which is 35.45. I'm going to multiply that by 2 since calcium chloride has 2 molecules of chlorine in it. I'm going to add those together, and that is my formula weight. We could do it for a bunch of other molecules. H2O, we have 1.01 times 2. That's the weight of hydrogen plus 16. We end up getting 18.02. Just a friendly reminder on how to do formula weight. Molecular weight is the same. So if we have a molecule like ethane, let's find the weight of ethane. Ethane is C2H6. We have 2 carbons multiplied by the weight of carbon, which is 12. We have 6 hydrogens. The weight of hydrogen is 1.01. Add that together, that's our molecular weight. So formula weight, molecular weight, we are finding the weight for compounds and molecules. Percent composition. Remember, we want to find the percent of an element in a compound. We're really just doing the part over the whole. So for a real easy example, if I take table salt as my example again, and I want to figure out what percent is sodium, I'm going to take the weight of NL divided by the weight of NaCl. That'll give me the decimal, and I can multiply by 100, and that will get me my percent. So remember, that's the easiest way to find percent composition is part over the whole. Here's an example using ethane again. Remember, ethane was given in the previous slide, but you've worked plenty with percent composition. Last little bit of math information that we need to use is we are still going to convert moles. Moles are our key unit, but how are we going to convert them, and what are we going to convert them to? Remember, moles can be converted to a variety of things. 1 mole is equal to the formula weight or molecular weight of that substance. 1 mole also has Avogadro's number, which is 6.02 times 10 to the 23rd atoms. 1 mole also takes up 22.4 liters of space of an ideal gas at STP. So 1 mole is the equivalent to lots of things. So Avogadro's number, 1 mole is 6.02 times 10 to the 23rd atoms or molecules. Molar mass, that's the weight of how much, that's the formula weight in 1 mole of a substance. So that's what we figure out. We do not use AMUs as much as we use in grams per mole as our unit, and that's kind of dealing with formula mass. So where we convert, remember, you really probably want to get down this idea. And we did the boxes last year, but where can you go? You can go from grams to moles, or moles to what we refer to atoms or molecules. Moles is always our base center unit. So if we go from grams to moles, we're going to use the molar mass. If we go from moles to atoms or atoms to moles, vice versa, we are going to use Avogadro's number. And we're going to kind of use that bridge to go back and forth. So mole relationships, we've kind of talked a little bit about this before. Nothing new here. Where we will pick up tomorrow, is the idea of how do we use the empirical formula and review a little bit of empirical formula and stoichiometry, but that will be in section 3.2.